Hello, this series of videos is meant to accompany the book Linear Algebra by Attorney Denton, Thomas, and Waldron. These authors are from University of California, Davis, and this is meant to supplement their book. So I have an outline that gives the highlights of Chapter 1. So I hope that watching this video will help you as you read the chapter. This is meant as a reader's guide, as I said, to hit the high points. All right, so first point they make is that linear algebra is the study of vectors and linear functions. So the first chapter is concerned with defining these concepts, vectors and linear functions. Now, you may have seen these before in previous math classes, but we want to generalize and kind of expand your horizons as to what a vector can mean and what a linear function can mean. All right, so if we go to section 1.2, vectors in the abstract are mathematical objects that can be rescaled and added. Okay, so let's amplify on that definition. I'll go to page 12. Page 12, here we go. All right, so look at these examples. Numbers. You have numbers can be added. Numbers can actually also be multiplied by scalars. That's pretty obvious. Okay. Now another example are three vectors. Well, you may have seen vectors in physics or in earlier math classes. They're basically represented as a list of numbers, sometimes as a column, sometimes as a row. Here we're going to often use columns because that turns out to be convenient. And vectors are added in this way, that you add corresponding components of the different lists to get the result. For instance, if I want to take 110 plus 011, I'm going to take 1 plus 0, and that's the first component of the result. 1 plus 1, that's the second component of the result. 0 plus 1, that's the third component of the result. So you add like components to arrive at the component of the result. Now you can also multiply vectors. If I took this vector 110 and multiplied by 3, what you do is you multiply each component by 0. So you get 3, 3, 0. If I took this 121 and multiplied by 7, I get 7, 14, 7. Okay, so this is another example of a mathematical object that can be added and multiplied. Other examples, polynomials can be added and they can be multiplied by a constant. I'm not talking about polynomial multiplication. I'm talking about multiplication of polynomials by a constant, by a number. Okay, polynomials can be multiplied, that's true, but we're not interested in that property right now. We're only interested in the addition and scalar multiplication property. My power series, similar. You can add them, you can multiply them. Functions you can add or multiply. All right, e to the x plus e to the minus x. It turns out that e to the x plus e to the minus x is a function called a hyperbolic cosine. You may or may not be familiar with that, but certainly you're familiar with adding and subtracting functions. X plus 2, that's an example of adding two functions, the function x and the function 2. Right? So all these examples have in common that you can add and multiply this type of mathematical object. I think there's another set of examples, the bulleted list at the bottom of page 14. We can go there quickly. I think it's more reiterating. This is just reiterating what we said before. Numbers, vectors of any size, not just 3 components, but we can have vectors of 4, 5, 6, 10, 200 components. And a vector with n components is called an n vector. We can do the same thing with polynomials of a given order, all polynomials, power series, functions of a certain domain. These all have the common property that you can add and scalar multiply each type of object listed here. All right, so that gives us a idea. That's our basic introduction to vectors. So you should think of that. Vectors in the abstract are this kind of object. But you can keep in the back of your mind this standard example of a column of numbers. It turns out that idea of a column of numbers is really very general, and many other situations can be represented as a column of numbers. For instance, we'll see that polynomials can be represented as a column of numbers. And even functions with a certain domain can be represented in some cases as a column of numbers. All right? So that takes care of section 1.2.